In this video, we're going to talk about section 5.5, multiple eigenvalue solutions, part 2. So we're going to complete the last 2 pages of this note section. So let me just begin by reminding you what we discussed in the previous video about section 5.5. And so in particular, I'm going to scroll down to the bottom of page 2, which explains how you're going to complete the eigenvalue method for solving systems where your defect is equal to 1. Remember, the defect is the term for the number of missing linearly independent eigenvalues when you're solving one of these problems. So what we're going to do is we're going to start with a repeated eigenvalue lambda. It, as an eigenvalue, has multiplicity 2. So if it's defective, the only way it could be defective is that it has defect 1. In other words, you're able to find one eigenvector, but then any other eigenvector would be linearly dependent to the one that you found. So what we want to do is we want to go ahead and find that non-zero eigenvector v1. And the important thing here is that you want to write it in generality. So you don't want to make a choice for any of your A, B, or C values. You just want to leave it in generality. This next step is going to force your values for V1. And so we have a system of 2 equations. The first one is find a non-zero eigenvector V2 that satisfies A minus lambda I squared times that vector gives you 0. And then furthermore, you're going to use that eigenvector to force out your first eigenvector. So notice the difference here is that now this is AI minus lambda V to the first power, multiply V2 by it, and that should force out V1. So this should be, this should be a nice check to see that that eigenvector V1 does in fact match the generality that we had written in statement 1. And then finally, you're going to form these 2 linearly independent solutions. The first one looks just like it always did, V1e to the lambda t. The second one becomes a linear combination. All right, and that's how we're going to get these 2 linearly independent solutions. So we had completed example 4 here in the notes in the previous video, and this was working with a system that had an eigenvalue of multiplicity 2, but defect 1. What we'd like to do in this video is to understand how we can handle this situation if we have a eigenvalue that is defective of order 2. So again, what that means is you have a multiplicity 3 eigenvalue. You can only find one linearly independent eigenvector. So you are missing 2 out of the 3. And so this system is going to tell you how to handle that. All right, so let's go ahead and start the same way we did for the defect 1 case. So you're going to find your eigenvalue, you're going to find the single non-zero eigenvector V1, and you're going to write it in generality. Again, that is super important. Write it in generality. Do not make any choices for A, B, or C. All right, so now we come to this chain of equations, very similar to what we had in the previous case. We want to go ahead and find a V3 such that A minus lambda I cubed, okay, an important difference, equals 0. And so I just want to call your attention to that 3 there. And then from here, once we get that V3, it's going to force down the choices for V2 and V1. And again, it's always a nice checkpoint to make sure that the V1 that you obtain is of the general form that you had found before. So if it's not, you need to reassess and perhaps you made a mistake. And then from here, we get 3 linearly independent solutions. Again, this first one is the same as before. X2 looks like our previous case, and then we have this new term here of a 1/2 V1t squared, and then linear combination of the others to form our third eigenvector. All right, so we're going to move on to the last example of the notes. I do want to warn you that it's fairly long, so there's only 1 page in the notes for this problem, but when I worked it out, I actually flipped it to the back page, the unnumbered page 6, and then worked the rest of the problem on there. So just know that that's coming. All right, so the first step we're going to do is we're going to find any eigenvalues that we might have. So let's set up our characteristic equation. Just to remind you, the characteristic equation is always the determinant of A minus lambda I equal to 0. So in this particular case, remember, I is the matrix with 1s across the diagonal and 0s elsewhere. So we're just going to subtract off lambda along all the diagonals. So I have -1 minus lambda, 0, 1, 0, -1 minus lambda, -1, 1, 1, -1 minus lambda. And this determinant must equal 0. All right, so again, I cannot stress enough that I know a lot of you guys are very familiar with the computation of the determinant using the diagonal products. And so adding the diagonal products on the standard diagonal and then subtracting off the off diagonals. And while that will still work in this case, because this is going to become a very complicated determinant, and we need to factor it in order to find its roots, I highly suggest you instead do cofactor expansion. So pick a row or a column to expand along, and that'll simplify your factorization once you're trying to find these roots. So I see 2 0 entries, so it's equally as good to expand along the first column as it is the first row. So it really doesn't matter, just make a choice. I'll choose the first row because quite often that's what we do in Calc 1 or Calc 3 when we're working with the cross product. And so let's start first with this first entry. So I'm going to copy that down. And by the way, this is a -1 to the 1 plus 1. So we'll get a positive sign there. Then what I'm going to do is I am going to strike through this row and column and then multiply by the determinant of the cofactor matrix. And now I'll move on to my next term. Now I have a -1 to the row 1, column 2, but look, now I'm working with the 0. So I'm just going to write the 0 there and then don't really care what that is because it's all going to go to 0. Finally, I have my -1 to the row 1, column 3. And the entry that I'm looking at now, let me actually delete these strike through lines as well. The entry that I'm looking at now is 1. And now let's strike through and write the determinant of the cofactor matrix. Okay. So now let's carry out these two determinants. We noted here that this is going to become a +1 and same here. So we don't need to worry about those. And so I have a -1 minus lambda times a -1 minus lambda times a -1 minus lambda, and then minus a -1, or in other words, +1. And then we had a 0, and then we had 0 minus a -1 minus lambda. All right, so here's where we're at so far. What I am going to do is I'm actually going to factor out any common factors I have in these 3 terms. And by 3 terms, I mean this term, and this term. Now, of course, we can just ignore that middle term because it's really nothing. But rather than just expanding everything out, remember our goal, and maybe I should add it over here, I have this equals 0, so I want to factor this completely. So there's no sense in multiplying things out when I actually want to factor it in the end. So what I'm going to recognize is there is a factor of -1 minus lambda in both of these terms. So let's pull that out front. And let's write in brackets what's left over. So let me just basically cross out what I have factored out. And of course, those become 1s. And so what I'm left with is a -1 minus lambda times a -1 minus lambda plus 1. And then remember, I have this -1 here on the end, so -1. And holy buckets, that's going to simplify right away. And so what I'm left with here is a -1 minus lambda cubed equals 3. So it kind of just factored for us as long as we were clever enough to recognize that we could factor out that common factor. So in this case, we conclude that lambda equals -1, and we have a multiplicity 3 for this eigenvalue. Now, at this moment in time, we do see that we have multiplicity 3, but we cannot say whether this eigenvalue is complete or defective. We cannot answer that question until we plug it back in and calculate any possible eigenvectors. So again, recall that we calculate an eigenvector by plugging in that eigenvalue, multiplying by some eigenvector, which we're going to call 1, and setting it equal to 0. So let's go ahead and do that in this case. I'm no longer using the straight lines because I want this to be a regular matrix, not a determinant. And I am now plugging in -1 where I previously had a lambda. So if I scroll up here for a moment and I look at this matrix right here, instead of -1 minus lambda along the diagonals, now I have a -1 minus a -1. In other words, -1 plus 1, which is 0. So I'm going to have zeros across the diagonal. And then I had a 0, 1 down here below. And let's fill in the other entries. 0, 1, 1, -1. 0, 1, 1, -1. Let me just make sure I got that all correct. And now I'm going to write my eigenvector in generality. Okay, and so now we want to see what information we can gather from this matrix system. So if I carry out the dot product, the first row times the first column would give me, would give me 0 plus 0 plus c equals 0. The second row times the first column gives me the same, 0 plus 0 plus c equals 0. And the bottom row gives me a minus b plus 0 equals 0. So out of these three equations, I can conclude the following. First, we see that c equals 0, and second, we see that a equals b. Now remember, I do not want to make any choices right now as far as my a and b values. C is forced for us, so we know c has to be 0, but let me write out my eigenvector in generality. My eigenvector v1 is a 0. And again, I'm just going to remind you, leave in generality. Okay, so what we've determined is, sure, we could choose a value for a, but if I choose a equals 1 and then try to find another vector, eigenvector, say a equals 2, those are linearly dependent because they're scalar multiples of each other. So we don't have enough eigenvectors, enough would be 3 in this case, to form our 3 linearly independent solutions. So at this point is when I can determine I have defect equal to 2. So we have 2 other eigenvectors that we need to come up with in order to come up with our 3 linearly independent solutions. So let's scroll back up here and see what we want to do. So the first formula that we want to work with is this one. I want to take a minus lambda I cubed times some v3 and make it equal 0. So the question becomes, what is A minus lambda I cubed? So A minus lambda I cubed is going to be this matrix that we just had up above. And then we want to multiply it by itself 3 times. Let me be clear by stating that I do not expect you to carry this out by hand. In the previous video, we did a 2 by 2 and we squared it because that wasn't very difficult. It's not that cubing a 3 by 3 is difficult, but it's certainly time consuming, and it's not what I'm trying to assess for your skills in this course. So I would prefer that you go ahead and utilize your graphing calculator and carry this out via your matrix calculations in your calculator. If you're uncertain how to do this, please let me know. Generally in class, I would show this up on a dot camera so that you guys could see how to enter in matrices and how to carry out matrix multiplication. Now that we're not face-to-face in course, I'm not gonna do that, but I'm happy to work with you over one of our Zoom meetings to do so. Else you can also Google it, and I'm sure there's plenty of wonderful YouTube videos to show you this. So what I'm going to do is I'm just going to say that, look, if I cube this, I actually get out the 0 matrix, and I'm just going to note this is by the calculator. So that way, whoever's reading my solution is going to understand how I got to that. So once you have shown that A minus lambda I cubed equals 0, remember, we want a non-zero eigenvector so that A minus lambda I cubed times this V3 equals 0. So that merits a happy face because that means that any non-zero vector is going to satisfy that. Any non-zero vector at all. So like I mentioned, it has to be non-zero. That's a forbidden vector. The only other vector we want to stay away from is any vector that's going to look similar to V1 because we don't really want it to be linearly dependent. So what I'm going to do is I'm going to make a choice . And I'm going to choose V3 to equal 1, 0, 0. Your V3 might look different than mine. Just make sure it's non-zero and make sure that it's not a multiple of V1. So now I'm going to move to the next equation. The next equation I want to look at is A minus lambda I V3 equals V2. We don't know anything about V2. We don't know what it looks like in generality. We have not discussed V2 whatsoever. So this equation is just going to force V2 right out for us. So let's carry this out by hand because we have lots of zeros here, so that's not going to be too bad. All right, so when I perform this matrix multiplication, what I want to stress here is that when I'm multiplying through by this vector, you'll notice that it's just going to pick off the first column because all of these are going to go to 0 because of these 2 zeros. So what I get is the vector 0, 0, 1. This is going to be my vector V2. So then finally, we want to come up with the last vector V1, which should look of the form AA0. And so let's carry out this multiplication. We still have our same A minus lambda I matrix. And now I'm multiplying by V2. And similar thing here, because I have 2 zeros and then a single 1 in the bottom row, that's just going to pick off my last column. So this becomes 1, 1, 0. This merits another smiley face because this fits with our generalization of V1 specifically for A equals 1. So now we're ready to write out our solutions. we have x1 of t equals v1 e to the lambda t, which is 110 e to the negative t. Now let's write out our x2. And let's remind ourselves of what that one looks like. All right, so we're looking at this equation, v1t plus v2, that whole quantity times e to the lambda t. So let's copy that down here. Way down here, v1t plus v2 e to the lambda t. And so in our case, that's going to give us 110t plus v2 was 001. That whole expression times e to the negative t. And I'm going to go ahead and just condense that a little bit, and I'll write it as t1 e to the negative t. All right, and so now we're off to our last linearly independent function. Let's scroll way back up here one last time. And now we're looking at this one, 1/2 v1t squared, and then going down v2t plus v3, all times that common exponential. All right, so we have 1/2 v1 squared plus back it up here. Let's put in our t, and then plus v2t plus v3 e to the, let's write it as lambda t. All right, so here's our general setup. Let's go ahead and set it up. So I have 1/2 of my v1, 110 t squared, plus v2 was 001 t plus 100, our choice for v3, e to the negative t. And so let's condense this to a 1/2 t squared plus 1, a 1/2 t squared, and a t. All right, so now what we have are our 3 linearly independent solutions. Remember that the final solution is always of the form x of t equals c1 x1 of t plus c2 x2 of t plus c3 x3 of t. And because the book typically writes their solutions in the scalar format, I will continue doing so. So I'm going to write it out in terms of x1 of t, x2 of t, and x3 of t. And notice that there are no vector hats on top of that x1, x2, x3 because they are scalars. All right, so let's write out our final solution. Let me zoom out so that I can see all of this here in the same screen. One thing that you'll note is all 3 of these solutions have the e to the negative t. So I'm just going to factor that out and leave it all the way at the very end. And so what I have is c1 plus c2t plus c3 times the quantity 1/2 t squared plus 1, all multiplied by e to the negative t. And so again, I'm just pulling off those top rows, but sticking in c1, c2, c3. And so then second row is going to be c1 plus c2t plus 1/2 c3t t squared, all multiplied by e to the negative t. And then the final one, we have no C1s. We have a C2 and a C3t e to the negative t. And that, my friends, is the final solution for this beast of a problem. All right, so that concludes our video here. We have now completed section 5.5. So make sure that you have looked at video 1 or part 1 of 5.5 as well as 5.2. And let me know if you have any questions in class.